So now we need to convert this guy into peak. So we divide it by 0.707. Okay? And then, Simon, what value do we get in peak? 818? Because I wanted it in peak to peak.
So like back at the top?
Back at the top, oops, right here, I wanted the answers in peak to peak. So as we're solving this guy, this gives us in volts peak, and now we got to do one more step to get it into peak to peak. And now we take that and we multiply it by 2. Yep, 26.36 volts peak to peak. Okay.
If you don't ask for it in peak to peak, you put it in RMS.
Yes, if it, yes. Well, it depends on what the answer is asking for.
So it's what it asks for, or RMS if it doesn't specify.
Yes.
So, I think I got it.
Okay.
Well, words aren't coming out, but it's kind of up there.
Okay.
One thing you have to watch for is watch if it says power, because that's the case you change to RMS.
Yeah, power, always in RMS, yes.
That's not like a confident you right there.
Did somebody from this side of the room? Okay, Zach. And how did you solve for it?
I did the just the voltage divider.
Okay.
It was 10.37K over 76.998K. Multiply that by 84. You get 11.313. So then you divide that by 0.707. Multiply that answer by 2. You get 32.003 voltage peak to peak. At an angle of 0.
At an angle of 0?
For voltage?
Mm-hmm.
Yeah.
Should be positive. Oh yeah, you're right. Should be 0.
I was like, wait, what? No. We're not there yet. No question. I was not going to
I was thinking I had the current stuck in my head. Those were flipping, but yes, you're right. Because when we have just the capacitance, we have multiply voltage and current, which is a positive and negative, or the current, which is a positive 90, and our reactance, which is negative 90. Those will cancel out. Yes, because they are at the same angle.
Oh, that's important too.
It's very important.
Don't forget that, guys.
Okay, so what's the answer, Dylan? Okay, so Dylan, you're running through it right now. What is the voltage at capacitor 3? 63. Okay, that's an RMS. What's our final peak to peak voltage? Once you get past these first couple of steps, if you're going to get it wrong, it's going to go way off once we get into these values. Unfortunately, the other ones you could get into the right answer. These ones there's just too many different calculation steps. Yes, Simon. How do we get to that one? Okay, so we have these are all the peak or the RMS voltages that we were given. So we subtracted them away from our total voltage, which was 84, which leaves us the 63.366. Right. So then to go from here into peak to peak, we have to take this value, so our voltage in RMS, multiply it by 2, and divide it by 0.707. Because taking the RMS voltage, dividing by 0.707, that's going to give you your voltage peak. Then we take the voltage peak and double it, and that gives us the peak to peak.
Unless that comes up really bad, it's not in peak to peak. What's up there and you're at 179 and I'm at like 20 and I'm like, huh. But it's because of the
Okay. Oh, you took the peak to peak volt values away from the 84. That's one thing that you got to be very, very careful to when you're writing these guys down. Make sure you label your units correctly. If it's RMS, put RMS. If it's peak to peak, put peak to peak. Even if you don't do it and on the test and stuff like that, they might not. Do it in your work. It'll help keep all your numbers straight with where you need to go. Okay. Questions about this one? Okay. So current total. So how do you solve for current? Voltage divided by resistance. And in this case, the resistance we have is reactance. Okay. So we have the 84 volts divided by the 77,000 ohms gives us the 1.091 milliamps. Then we can take that value and plug it in to solve for voltage like you did on this one. Because the current in a series circuit is what? The same. So everywhere is going to have total current. We could also solve these guys using voltage divider, which is what we used for VC2. Because everything is in the same phase angle, so we can use voltage divider. Once the phase angles start changing, we cannot use voltage divider anymore. It will not help us. Because these things do not add together linearly. Now we're looking at the quadratic equation. The Pythagorean's theorem. You will use the quadratic equation later, just not right now. Okay. Questions about that? Oh, the capacitance total? Okay. So in a series circuit, capacitors we treat like they're in parallel. Well, we add the inverses of them together. So we add the inverses together, get them all together, and then we take the inverse of that, and that's going to give us the 75. Just as if that was resistance values in parallel. And because they're in parallel, they're going to be less than the smallest value, which is 100 picofarads. People smarter than me. Ohm, Edison, Tesla, Ampere, Watts, all those guys that came up with this stuff, they were all dreaming of this stuff. Okay. The what?
When I asked for the current of the capacitor instead of when it went to the voltage, I forgot that there was a current, so I was like, oh, it's 0. It's not 0 degrees.
It's not.
Oh, wait, the degrees get changed again?
No, we're good for right now.
Oh, thank God. Hallelujah. Oh, well, thank God. You have to have it like that.
Okay. Biggest things we want to look for on this guy is our capacitance total, the current total, current of C2, current of C3, the voltage of capacitor 1, voltage of capacitor 2, and the voltage of capacitor 3 and 4, because they will be the same.
What is this weird deep thing off of?
Why is the voltage across 3 and 4 the same? Because it's 2 and 3?
Yeah, that's what I meant. 2 and 3. 2 and 3.
I was really confused because I was like, what the heck?
So voltage capacitor 3 and 2 units. So that separates.
Yeah, basically, what's the voltage of these guys? What's the voltage of him? What's the voltage of him? Current, and then the branch currents. What, this guy?
What?
This?
Yeah,
These are micro.
Yeah, I know, but when you take the total, it's going to be nano.
Shouldn't be.
Close ones.
Oh, actually, yeah, it might be. It might be.
Okay, but who decided that the little symbol for nano or micro should be really close to the symbol for pico?
Because it comes from the word mu. That's why.
Well,
That's
like,
the Greek letter mu.
But like they look very similar.
They do.
Where's in Greek it doesn't, because this language didn't exist then.
Yeah.
It was blame the Arabics for that if you want. That's why they look so similar.
You can't blame them because they're Arabic.
Huh?
We're using Arabic numerals though.
No, we can't blame the Arabic. We can blame
The X?
we can blame
Reactants?
mathematicians.
No, you still. So that's the thing is, these are just the answers that I want. Yes. Yes. This is just the answers I want.
Yeah, I got you. Yeah, we both gotta be careful. Might backfire.
17,
Really?
38,
296.
420.
Oh my god.
Oh, yeah, that's what I got too.
Did you say negative? Oh no, that's normal.
Do what now? You got to find the reactants.
What range?
C2 and C3 are added together in parallel with.
Right.
Yeah, because remember they're capacitors.
Right.
Do you want the voltage of C1 in,
Always an RMS.
Yep, RMS unless otherwise. Yep. This one we're not going to do the extra steps.
Make sure I wrote this right.
calculator clicks go a lot louder in the library?
Yeah.
No,
They do. They do.
Actually typing in into your calculator, like a random, like, what's going on?
Something's gonna blow up.
That sounds the source of a ticking noise. It's a pipe bomb.
Huh? I'm not sure exactly what it was that blew up this time. No, it didn't.
He fell over.
Yeah.
Well, Ryan just fell over
Yeah. Well, I mean, it startled me because I saw the flash out of the corner out of my eye, and then heard the bang at the same time. So that's called that. What that happened? That's called an arc flash, and that can be very, very deadly in industry. Very deadly.
Is that like the video that you showed us?
Yes. Yeah, that's arc flash.
Well, I wanna know the answer to that. You'll miss it one video.
I just took out the server board and then you put it in, and it was like create that huge flash.
You know all the companies when I'm gone?
Not intentionally.
Oh, this was at the start? That makes sense.
That's not right. Yeah, that is right.
You'll treat them just like normal. So your reactants will add for here. These two will be in parallel, and then you'll add that value to those two. Yeah, the capacitance you treat as the opposite, but the reactants you treat regularly like resistance. Right, they're still going to have the series and parallel rules applied to them.
You know, I thought it turned out pretty good. I was pretty happy with it.
So we're solving for everything this time?
Just those guys.